Srinivas sir. So for the past days, we have very deep insights into the signal processing and communication systems using FPGA. So today is the last day. So we hope the same will continue today with more important topics. Uh, so with this, I warmly welcome the resource person. Sir, you can please take over the session.
Okay, sir. Thank you very much. Good morning, all the participants. Welcome to the day 5. That is the last day of our FTP. I hope you are having a wonderful journey while exploring the concept of digital VLSI system design implementation using FPGAs. So we shall resume our experiment that we are doing yesterday that we have stopped in between. So before that, let me allow me to share the screen. Yeah, I hope my screen is visible to you. So if you remember yesterday we were designing a data source. So it has a clock input, reset input, and we are giving a start trigger input. Whenever we are giving a start trigger input, what it is doing is inside the data source we are putting a small memory kind of an element, where in this memory element we are storing the signal samples. So when the start is triggered, what it is doing is we have already designed the frame energy module, right, to compute the energy of a signal. So whether that module is in idle state or a busy state, that is the data source is checking the frame energy module status on this feedback signal, that is ready status. Once the frame energy module is ready, what our data source is doing is it is giving a start trigger signal to the frame energy module. Once a start trigger is given, the frame energy module is switching from idle state to the computation state. Soon after switching into the computation state, what our frame energy module is doing, it is waiting for the signal samples to arrive. So what our data source is doing is it is sampling, it is providing the signal samples to our frame energy module via the data sample input. And whenever the data source is providing a sample, it is acknowledging the frame energy module with an acknowledgement signal, that is data valid. That is nothing but a small pulse of duration equal to one clock cycle. So in this way, what our data source is trying to do is read all the samples one by one from the memory and sample it on the data sample output at a rate of one sample per clock cycle. So once these samples are sent out to the frame energy module, so we will be integrating that frame energy module, right? So the frame energy module receives all these samples, and we know that to the frame energy module we are giving one input called frame size. So depending upon the frame size, what it will do, it will collect those many number of samples, and what it is doing is it is calculating the energy of the signal. So this is one signal processing application that we are interested to put it on FPGA and verify its functionality. So our design with respect to frame energy module is already ready. So only thing is we need to make the data source to be ready. Once the data source is ready, what we'll do, we will integrate these two things and then we will put it on FPGA. So if you resume back, so yesterday we just created a FSM template to develop a data source. So we have a data source module. So whatever the inputs and outputs that I have shown here on this screen. So for that, what we have done, we have defined a port list, clock reset, starting, and ready input, that is ready status frame energy, and start output, data sample, data valid. So we assumed that this is a FSM with the 4 different states. And what we have done, we have three outputs, right? So for all these three outputs, we have designed the registers that are driven by the equivalent combinational next state logic. So what we have done, those registers we have defined in the sequential state register logic uh, under reset condition, and when reset condition is not available, what it is supposed to do. Next, in the combination next state logic, we have defined again the default conditions. After that, we have written the case statement, and we are supposed to define the functionality of the FSM in 4 different states, that is S0, S1, S2 and S3. And finally the output logic, that is the data flow modeling. What we have done, the outputs we are driven with their respective registers. Now we have to define the functionality of our module, right? So before that, I already mentioned you earlier that inside the data source we are using a small kind of a memory element, where in that memory element we are storing the data. So first allow me to create a memory file. So here I told you earlier, on FPGA we have block RAM resources that can be configured to realize memory. So what I'm doing is I am instantiating a block RAM in order to store the data. So there is a primitive in Vivado. So how to just refer to a block RAM in your design. So for that, what you have to do is so in the parenthesis, this is a syntax. You just take a note of it. So first we have to define what is a RAM style is equals to block. Actually, there are two RAM styles. That is, one is block that uses a block RAM resource in the FPGA in order to construct your memory block. Otherwise, there is another RAM style that is called as distributed, distribu. The distributed is used when this distributed keyword is used, then it won't use a block RAM resource. Instead, it will use the basic building block, that is configurable logic block, CLB. Inside CLB we have slices. I told each slice can be used as a logic or as a memory. If it is used as a logic, then that slice is called slice L. If it is used as a memory, it is called as slice M. So the basic building blocks, that is configurable logic blocks, inside the configurable logic blocks, if slices are used in order to realize a memory kind of an element, that type of memory we call it as a distributed memory. So if you realize a distributed memory, more number of resources will be used on FPGA. Instead, in order to reduce the utilization of the resources, what we can do is we can use block RAM. So a single block RAM resource will be used instead of the basic building blocks. So again, yesterday I told memories you have to create by using a reg data type. And in a reg data type, first you have to define what is the word size of each memory. So earlier I told you, right, memory is a two-dimensional block. So it has rows and it has columns. So signals are placed across the rows, and the columns means represents the bit positions of each and every uh, uh, bit positions of a respective word. So here our sample length is 16 bits, right? So we'll take the word size to be 15 down to 0. And a memory name, you can give any name. So by default, for convenience, I am just referring it to a variable name, that is m. And what is the depth of the memory? That is varying from 0 to maybe as how many number of samples that you want to store in memory, those many number of samples you can store. For this simulation purpose, what I am doing is I am taking a frame depth, I'm taking a memory depth to be 7. So total I want to store 8 samples in the memory. Why? Because we have seen an example, right? We have chosen a frame size to be 8, and for that frame size 8, what we have done, we have given 8 samples that corresponds to a speech frame, maybe a signal. So for that 8 samples we calculated the energy. So in the similar way, what we do is we create a memory with a depth of 8 locations, and in 8 locations we will store 8 samples. Maybe we treat these 8 samples as a one signal. And to the signal, what we'll do, we'll try to calculate the signal energy. So this is a configuration of the memory. Now what we do is uh, we try to code our describe the functionality of our FSM. So when we are describing the functionality of FSM, so first we will begin with the S0 state. It has to scan the start input of the data source. So it has to check whether any trigger signal is coming on the starting signal. Start, so begin and end. So if any start signal is coming on the data source, then what it has to do, obviously the FSM should switch to the next state, so that we represent as state underscore S1. So it should switch to state. So once it is switching to the S1 state, uh, so there are no other operations that it needs to do in S1 state. So there is only one operation. So that's it. If start is not coming, it will remain in the S0 state. That means next state is equals to present state. So that is by the default condition. Anyhow, it is fulfilled. So you need not write if start, then go to state 1. Otherwise, you need not write else state next equal to S0. Why? Because by default state next equal to state rich. Hello, I'm getting some. Am I? My voice is audible, right?
Yes, sir. You're clearly audible.
Okay. I got some few disturbance, so I am worried again it got disconnected or not. Okay, fine. So this is the S1 S0 state behavior. After switching to the S1 state, whatever data source has to do is it should not start the data transfer immediately. First, it should check the status of the frame energy module on the ready input. When the frame energy block is ready, then only what our module has to do, it has to initiate the data transfer. So what we are doing in the S1 state, we are scanning the ready signal. So in our case, the ready signal input is ready status of frame energy, right? So this I will copy and I will paste it over here. So it is scanning the status of the signal. So if it is ready, then what it has to do, it has to initiate the data transfer. The data transfer process that will carry out in the S2 state, not in the S1 state. So for that purpose, what we are doing, we are asking the FSM to from S1 to S2. When after entering into the S1 state, it will check the status of the frame energy block. If the frame energy is ready, then what it is doing, it is switching to the S2 state. And at the same time, what our module is supposed to do, it should also trigger the frame energy module, indicating that the data source is about to initiate a data transfer, and the frame energy module is supposed to receive the data and calculate the frame energy. So how the frame energy will know the data source is going to initiate a data transfer? So frame energy should be triggered. So how that triggering will happen? Uh, the data source, what it has to do, start out should be made to be logic high. So in the S2 state, what we are doing is we are making this start out underscore out to be logic high. So we do is start underscore out underscore next. That is combinational next state logic we will update to the 1 tick B. So on the arrival of the next clock edge, this combinational next state logic will go to sequential state register logic, that is start underscore out underscore reg. So in this register we will get. So soon after the register is updated, this register will drive the output. That is start underscore out underscore reg will drive the start out. So in this way, when the start out is driven, anyhow this is connected to the start input of the frame energy module. So it will trigger the frame energy block. So no need to write the else part. If suppose our frame energy module is not in the idle state, so data source will not initiate the data transfer. However, it will wait for the frame energy module to become ready. So until then, unless it becomes ready, it will remain in the S1 state. So you need not write the else part. Why? Because by default you have written like if by default operation, if none of these operations are valid in the S1 state, what it will do, the state next is nothing but state reg. So it will FSM will remain in the S1 state until the ready status is logic high. Now in the S2 state, what we do is if you see here in the S1 state, what we have done, we have triggered our FSM, sorry, the frame energy module. So once you trigger, the trigger should be like a short duration pulse. Maybe this pulse should be of 1 clock cycle duration. So since we made this start out to be logic high in the S1 in the S2 in the S1 state, if you remember, if you in the S1 state, what we have made, the start out is we made it as logic 1. So from logic 0 we made it as logic 1. If you leave it like this, it will be logic high for the infinity number of time. But as per the convention, it has to be high for only 1 clock cycle. It should look like a pulse. So what we have to do now, it is our responsibility to make this logic 0. So that how we will do is in the S2 state, we don't do any other operation. What we do, first we will make a start out to be 0. And then what we are doing is we are switching to the S3 state. So our actual data transfer mechanism will be carried out in the S3 state. So after making the start out signal to be logic low, what you are doing is you are making a state transition. So you are jumping from the S2 state to the S3 state. Now in the S3 state, the actual data transfer mechanism should start. So how we will define this data transfer mechanism? Just wait a minute. Just give me a minute. Yeah, what it is supposed to do. Now we want to sample the data in each and every clock cycle. So for that, so first data sample, right? So sample the index, right? So for that we require an address. So to determine the address, again we require an depth of the memory, total 8 locations. To represent 8 locations, we require 3 bits. Address underscore reg, and we need an address register. So we are doing register. And this register will be updated by the next state logic, and the ideal case a combination next. And now here what we are doing is data sample reading from the address value present in the address register. Data sample next equal to memory of address list, and once data sample is read, what we have to data sample valid to be logic high. So and next address also needs to be incremented, right? So next one, the address register. Okay. To it is reaching to the maximum count value, that is what is the maximum depth, that is 7, right? So just a maximum value, and value should be reset to 0. So state transition from data transfer is completed. What we Okay, we will run the simulation and check whether it is not an issue. Okay, so once it is entered into the S3 step, what it is doing, it is reading the value from the memory at address location from the address register. That value is kept in the data sample next, and data value next is made to be 1. So initially address value is 0, so 0 sample is that data value is made 1, and then address will be incremented by 1. In next clock cycle, first sample will be read, data next will be 1. Address will be incremented in the second sample. So actually I can get this address register. Should be okay. So I think we are done with the description. I have just small doubt only from the simulation only we can come to know. So what we can do is, I think if you have completed the description along with me in the Vivado, so you can just write a test bench and then try to check it by using the. So let me allow me to create a file project. So therefore, lab you can just add it in your project if you have not added. So lab net is also service data source. I will just make the font size to be large. Okay, so this is our data source. Yeah, we have instantiated the VRAM, right? But we have not defined the file through which it has to take the data. So that initialization step. VRAM declaration. In a VRAM, now we have to initialize. We have to write initial beginning point. So I'm initializing the VRAM, reading memory binary, and the file I have to use the entire path. Data file having a file extension called .mem, and this data in the memory file should be loaded into the memory that we have created, and that memory name is capital M. So the memory is 0, the memory is 7. Yeah, so earlier, now we have to do, what we have to do is we have to create a memory file. So earlier we have only created Verilog source files, right? So if you click on add sources, click on design sources, click on next. Here there is an option called create. So while creating, it is asking you what is the file type. So at the bottom, if you click on this drop down menu, at the bottom you will have a memory file. So you click on the memory file. Once it generates a memory file, it will by default it will generate a file with .mem extension. So my memory file name is memdata. So I will save it. So you can see memdata.mem has been created. Click on finish. So under the design sources, you will get a folder called memory file. Inside that folder, you will have memdata.mem file. So this is the memdata.mem file I have initialized here. So whatever the data that is available on this file, you will read it and it will initialize in the block RAM. So from where I will get this data? Yesterday I think we have created a test bench, right? Data in context. Sources. If you remember yesterday we saved the data, right? For the test bench, for the purpose of test bench, what we did, we created a file and we loaded it into a test bench. So now what I'm doing is that data, same data that I'm in the memory. So that is a RAM that I'm going to initialize. So one thing I have to do plot is, so we will quickly write a test bench for this. So what is the template for the test bench? First we have to declare the inputs. Next we have DUT instantiation. So inputs should be wire data type. DUT instantiation. So we need to add a so we need to what is inputs. So clock is equals to 0. Next we need to generate first reset. How do we do we just next status. Leave it, no problem. So we just launch the simulation. So let's check the getting. So this data center we have to put in products signed. I think 1, 2, 3, 4, 5, 6, 7. So this example when it is coming, the data value is 0. So that is a problem we are having. And this data value now we will run. I think now it is fine. So we give reset, we removed the reset, we triggered start signal. but ready of the frame sample is not frames framing module is, sorry, frame energy module is not ready, so it is ready, we made ready over here. After that, once it is ready, what we did, we triggered the frame energy module. After triggering, we started giving the data samples. So 0.5 is when the first sample is coming, data value is high. Second sample, data value is high. 4, 5, 6, 7, and 8. So this is also valid for one clock cycle. After that, data value is 0, indicating that the data transfer has stopped. And after some time, since again the start is triggered continuously, the data source we are triggering it. I mean, it's not like a trigger, we gave the start input continuously to be 1. So again, it starts to transfer the same data once again. It is trying to reinitiate the data transfer. However, the ready frame energy, some frame energy module is also ready. Then what it is doing again, it is making it start out to be, it is triggering the again frame energy, and again from this timestamp to this time, again it is initiating the data transfer, and in each and every block cycle, it is giving one sample. So I think it's working fine. So our data source is working as per desired function. Just a minute, please hold on. I'm getting a Yeah, from the simulation, we can see that our data source is performing the task of data transmission. So whatever the fixed amount of signal samples that we have stored, it is streaming them on this data output, data sample output. So now what we can do is we can perform the block level design, wherein this data source can be integrated with the frame energy module that we have designed earlier, and then we try to implement it on FPGA. So since the simulation is passed, let me check whether we are able to synthesize it and we are able to get a gate level netlist or RTL netlist, equivalent netlist for this description. Only thing, in order to confirm that there is no problem in my HDL description. So if the synthesis is perfectly fine without zero errors and warnings, without any errors and warnings, then I can assure like RTL is valid, RTL description is valid. Hmm. Now what I will do is I think you might be having the frame energy module design verilog file with you people. If you people have already done it, so well and good. Otherwise, I will do one thing. I will share that file along with this file. So we will do hardware implementation for this one. So the synthesis is successful. There are no errors and warnings. So now we are safe to use the data source module. So just to give me some time, I will just share these two files to you. If you have done designing the data source as well as frame energy block, you are free to use your own design. Or else those who are lagging, what they can do is, in order to follow today's experiment, what I will do is I will share the day for lab 1 file, that is frame energy module design file that we have done yesterday, along with the data source module file uh, to Mahesh sir. You please collect from him. So I'm just stopping the presentation over here. I'm just sharing the files. After that, again, I will resume the presentation in another 2 minutes. I request all the participants to wait. declare the inputs. Next, PUT instantiation. So welcome back participants. I have shared three different files to Mahesh sir. Kindly please collect all these files, and now I will guide you to the step-by-step procedure for hardware implementation. So it is more or less the same that what we have seen on all these 4 days of our journey. So I will once again just guide you through the process. Just try to follow it up along with me. So we are going to create a new project. So this is lab 3 of day 4. Uh, I'm using general purpose RTX 7 basis tree FPGA. So I create a project. Make sure the project target language is Verilog. If it is showing VHDL, just change it to Verilog. And next click on add sources. Instead of creating the source, now you click on add sources. As I have provided the files to Mahesh sir, you please take them. So from day 4 lab 1, what we have done is we have created a frame energy block module, nothing but to calculate the energy of a signal. It's a hardware module to calculate energy of a signal. To please add that. And next, in today we have seen how to design a data source block. So that is lab 2. So from the sources, what you can do, so that is data source.v. You can add that. There is a mem file that I have given. So that is memdata.mem. So just add that as well. So you add all these three files into your directory, into your project. So under the design sources, you can see all these three files. Now what you can do is you can click on create block design and click on, may keep the name design_1, click OK. Now you click on, now a block design environment has been created. So what you can do is you can click on the sources. So first add a frame energy block. So right click on it and click on add module to block design. So once double click on it, so there are no anyhow customization parameters. Okay. And now what you can do is click on plus icon, just add the clocking wizard IP. Just type clocking. So clocking wizard IP core. You just customize the clocking wizard IP core. Maybe you can click on output clocks. You can choose any of your desired frequency. Maybe I will choose 75 megahertz. I'll click on OK. Now what I do is out clock underscore in one port, I will make it external and I rename it as clock. Next, similarly, the reset signal I will make it as external and I rename it as reset. And this clock out one I just connected to clock. locked output I connected to active low reset. And next, what I'm doing is I'm adding the data source. So right click on it and click on add module to block design. So this is a data source. So to this data source, provide the same clock from the clocking wizard and locked output of clocking wizard to active low reset. Next, what we are doing is in the data source we have a start underscore in, right? So that what you can do is you connect it to a constant. So click on plus and click on constant. So this is constant is nothing but a built-in IP core. Once again, as the name suggests, it will give you a constant value. We permanently connect start a underscore into 1. That means we are continuously making the start input of the data source to be logic high, so that it will try to continuously stream the data in the form of a data packets continuously to the frame energy for infinity period of time. Next, the frame energy ready output needs to be connected to the ready status frame energy input of the data source. That's the feedback output. So through this output only it will scan the status of the frame energy module. When the frame energy module is ready, then only what it will do, it will start the data transfer. The data source will initiate the data transfer. So before initiating the data transfer, first what data source will do, it will trigger the frame energy module. So the triggering will happen from the output of start underscore out of data source that is connected to the start input of the frame energy module. So after the frame energy module is triggered, the frame energy module will switch from idle mode to the computation mode. In the computation mode, the frame energy module will wait for the data samples to arrive from the data source. So now connect the data sample output of the data source to the frame sample input of the frame energy module. And how our frame energy module will know whether a valid sample has arrived or not. So data source, whenever it is providing a data sample, it will acknowledge the frame energy module by a data valid signal. So that data valid signal should be connected to the frame sample valid signal. So we rearrange the block. So that's it. And the frame energy, we need one more input is pending, right? This frame energy, what is the frame size? So that frame size, what we are doing is it has to be by default. Currently we are setting it to 8. Why? Because in our data source we have only 8 set of samples that is treated as to be one frame or a signal with a duration of the signal with a size of 8 samples. So the frame size needs to be 8. So again we can take some constant IP. You can configure this. To represent 8 we require 4 bits, right? uh, and the value is 8. So you click on OK. So the tree is okay, sorry, but if you see the frame size, data work is 10 down to 0, that is 11 bits. So here we keep a constant width to be 11 and the value is binary 8. Just a minute, I'm just referring to the manual of the constant IP. Okay, the supportive formats is decimal, binary, octal, and hexadecimal formats. Okay. Okay. Even decimal format is supported, but it equivalent binary will go. Okay. So the frame size is also set. Now what we have to do is we have to observe the energy value and these things, right? To observe that, we will add ILA IP core. Just a minute. Yeah, sorry for the interruption. So we'll customize the ILA IP core. The interface type is native, and we want only two probes. And sample data depth by default I'll keep on 024. And what is port size? Probe size. First probe I want it to be 25 bit. Second probe is 1 bit. So I'll click on OK. To the clock input, what I do from the clocking wizard, I connect the clock, and the energy value. What I do is I connected to probe 0 of ILA, and the energy valid that I connected to probe 1. So I just rearrange the diagram and I go. In Vivado, we have many different views of the block design. If you see, this is a default view of the block design. If you think like this is little bit clumsy, then here there is a drop down menu. There are different other modes to visualize this block design. So you can click on interface view. I think interface view will not work here. You can click on reduce jogs. So the jogs will be reduced. If you click on no loops, loops will be avoided. If you click on grouping and no loops, so this is one type of a view. If you click on colored, you will get some color coded kind of view. There is no addressing view. Okay, so this is the default view. In the default view, all the inputs of any block will be towards left and all the outputs will be towards the right. So if you click on no loops, the position of inputs and outputs will be shuffled. So in order to avoid a looping kind of diagram. So for simplicity purpose, I will leave it to default view. So I'll just rearrange the design so everything is fine. So now what I will do is I will click on validation. I will run validation. So validation is successful. There are no errors. So now what I will do is I will save the block design. So after saving it, I will click on the block design and right click and click on generate output products and click generate. So now a Verilog codes for each and every IP block what we have done, the Verilog codes will be generated at the back end. Once the Verilog codes are generated, then we have to make our top wrapper. So now Verilog codes will be generated and it will be synthesized, and synthesized netlist will be generated at the back end when you are running the output product generation. So this will take some little bit time, so we will wait until the process is completed. So you can just open the log to check how the process is going on. So this time we have not used any VI or IP. So directly we used constant IP blocks instead to drive the constant values, and ILA IP core is used to monitor the outputs. So frame energy clocking wizard and data source output product generation has been completed. Now it is performing for the ILA IP core. So all the IP cores has been processed and output products are generated. So now we'll click on the block design and we'll click on right click, and what we'll do, we'll create a HTL wrapper, and we will let the Vivado manage the wrapper and auto update. So it is just updating. So wrapper has been generated and updated, and it is set to as the top module. So if you just open the wrapper, you can see the block design and the instantiation. And if you further open, you can see the data source block and as well as the frame energy block. So now what we do is we will create a constraints file for our clock and reset. So for that we click on add sources, add or create constraints. So click on constraints. Design underscore dot xdc. So the constraints file has been created. Now what I will do, I will go to base stream master xdc file. xdc file, what I will do is I will add the constraints for the clock and the reset signal. So I just copied the clock signal constraints. So these are the clock signal constraints, and in the diagram you can see the clock is pin name is clock. So I'll replace with CLOCK clock. So input clock is connected to the onboard crystal oscillator. The clock is connected to the clock pin W5 of FPGA. So from this clock, which is operating at 100 megahertz, I'm connected to the clocking wizard IP core. From this, I'm deriving a clock with 75 megahertz, and with the 75 megahertz, I'm running my entire reset. So these are the clock constraints. Now so for that I will configure it by using a push button. So I'll just copy the constraints of a center push button on the basis FPGA board. So I'll just paste it, uncomment, and button C I will replace with key name. So reset is RESCT is connected to the U18 pin. So the constraints are ready. I just saved it. Now we are free to run the synthesis and implementation. So I clicked on synthesis. So first let the synthesis be complete. So after the synthesis we'll proceed with the implementation. I hope everyone are following along with me. Even if you are a bit slow, no need to worry. I think the sessions are recorded, right? You can just go back and complete the process. My main intention is you need to understand this flow. Even if you're not able to do at a fast rate as I am doing, that's okay, not an issue. The motivation of FTP is to learn all the new concepts and all. So familiarize with all these new concepts and practice as per your convenience. So synthesis is complete. There are no critical warnings or errors. So I'm just running the implementation process. Yes. Anyone has any doubt?
No, sir. Please continue.
Okay. Sir. So implementation is completed with 0, 1x, 0 critical errors and 0 errors. So now we proceed with the bitstream generation. So as you can see, with the increase in the complexity of the design, the amount of time taken for synthesis and implementation and for bitstream generation keep on increases with the complexity of the design. So generation to complete all this process, it also depends upon the hardware configuration of your system. So you need to have a lot of patience and you need to bear with the process to complete. So at the back end, there are several type of optimization algorithms that will be running in order to do a proper placement routing of your synthesizer netlist. So for very high-end designs, even our personal computer will not be supported to perform all these kind of designs. So generally, uh, in case of VLSI designs and all, we typically rely on workstations. Uh, Even the fab labs and all, they have their own dedicated data centers in order to run all these kind of programs. In order to run all this kind of a process for a typical ASIC design or else any kind of a processor that they are going to design, maybe a general purpose laptop processor or else maybe a mobile processor. So this is how the complexity of a VLSI looks like. So the bitstream generation has been completed successfully. Now I just open the hardware manager and try to connect the target which is available with me. Even you can also just try to uh, do the bitstream implementation by connecting the basis to FPGA board. If anyone is having difficulty in generating the bitstream, I will share you the bitstream file. You can directly dump it on FPGA and check it. So let me check whether my bitstream is working as per the desired function. So as you can see on the screen in front of the camera, I have connected basis to FPGA board to my host computer. Uh, Now I click on open target and click on auto commit. So it is trying to establish a TCP IP connection with the board. So the connection was established. The connection is established. So the device drivers were able to recognize the board that I connected to my host computer. Now I click on the program device. And on the screen you can see there is a bitstream file along with a debug probes file. So I will just dump all these two files. Okay, the program is successful. Now I got the ILA window. I'll just run the trigger. So it seems like I got some output. Just a minute. Yeah, I'll just zoom it. This is a frame energy, that is a signal energy you can consider. Signal of finite length duration, where the finite length sequence is nothing but a sequence of 8 samples. So I'll change the radix. So unfortunately, in the latest versions, I don't know. In the ILA core, they removed the option of real number representation. Only binary, hexadecimal, octal, hex, ASCII, and unsigned decimal and signed decimal is there. So no problem. What we do is anyhow, I have a MATLAB script, right? So from that we will try to verify. If you're working with the old version, I think in the ILA you will be having option to change the radix and represent it into a real number format. So close. So let me open my MATLAB script. So this is a MATLAB script. I think I have given the sequence 2, that is frame 2 data. So for the frame 2, the energy value is 0.5253. So what we have to do is we have to convert. I think first we need to give word size, right? Let me check the syntax. Word size followed by the fractional length. So word size here for the energy. Here we have represented in 25 bits, right? So 20 fractional length is 14. And now uh, 000219F, but I think we got different answer. 21. Yeah, same. So the MATLAB is giving the value as you can see it is 000219F in hexadecimal. On the hardware, when we have run through the data source, what we did, we have given the data samples 0 0.5, 0, minus 0 0.25, 0 0.2, minus 0 0.0625, 0 0.0625, minus 0 0.2, 0 0.25, and minus 0.25. That is a signal with 8 samples. To this, for this, the energy that is calculated in MATLAB is 0.5253. This if we represent in unsigned fixed point format with a bit length of 25 bits, having 14 fractional bits and 11 integer bits, the value in hexadecimal is 000219F. The same thing when computed in hardware, it is 000219E. Instead of F, we got E. Why? Because due to truncation error. Because MATLAB has calculated the value in floating point, and that floating point is being converted into fixed point. But in our hardware, what we did is even the signal sample values are also in fixed point. That fixed point values we have used to compute the energy. So we got almost nearly equal. So the error is very small. So we are able to calculate the energy value accurately. So what you can see here, the data source is continuously streaming the samples. So like in the form of a data packets, it's a continuous data transmission. So what our module is doing, each and every data packet it is taking and then trying to calculate the energy, and the calculated output is given here as follows. So the MATLAB output energy value computed on hardware, it is corroborated with the output in MATLAB, and the results were matched, and a hardware module what we have designed, it is working in real time with the desired functionality for which it is intended for. So this is a real-time example of a digital signal processing application. So this the application that we designed, it is mainly used in speech signal processing applications, where in speech signal processing we'll have a continuous signal. That signal will break it in the form of a frames. Each frame is having a finite length samples, and in speech signal analysis there is one parameter called as frame energy. In order to calculate the energy, what we do is energy of a particular frame, what we do is we give a frame and we square all the samples within the frame, and then we do a running sum to calculate the energy value. So this is a real-time application, and we have implemented on FPGA and we have tested it. So with this, I conclude this presentation with respect to this experiment. I hope I am clear with respect to this presentation. If anyone has any doubts, then I can just address them. If you people have still doing, or else or still lacking, or if you want to do this implementation, one thing I can do, I can provide the bitstream files, so that instead of you can directly dump the bitstream file into your FPGA and you can verify the outputs for time being.
Sir, actually, they are trying to do.
Okay,
However, you please share. If they are unable to do, then I will share the bitstream file.
Okay, sir.
Then you can continue, sir.
Okay, sir. We will take a short break, maybe some 10 minutes or 15 minutes. After that, I will just explain you a new concept. Earlier, I told like it is also, we have seen how to use the inbuilt IP cores. Earlier, I told like even we can develop our own IP core from our hardware description. So that is a very much important topic in the current scenario. So I will just present a small example and I will show how to design a user-defined custom IP course. So before proceeding to that, you can just take a small break. In the meantime, I will look for the bitstream files and I will try to share it to Dr. Mahesh sir. You can collect from him and try to do the implementation.
Hello, sir.
Yeah, tell me, sir. Hello.
Sir, please tell me.
Yeah, tell me, sir. You have any doubts?
No, no, nothing. You can continue.
Yes, yes, sir. So, shall I begin the next session?
Yes, yes, please.
Okay, okay. Just to give me some time. Yeah, dear participants, kindly please pay your attention over here. I have shared the .bit file and .ltx file for the design that we have done just now. So in order to directly run the bitstream file, so I'll just show you how to do it. You just create any blank project. Don't add any sources, anything. Just create a blank source, blank project environment. So there are no sources, as you can see. You can directly click on Open Hardware Manager and connect your FPGA. Click on Open Target and click on Auto Connect. So first it will identify the board. Once the board has been identified, then what you can do is you click on Program Device, and it will ask you the files of bitstream file and debug probes file. So whatever the files that I have provided, you just source them. In the bitstream file, just source the bitstream file. In the debug probes file, you source the debug probes file. So bitstream file will have an extension called .bit, and debug probes file will have an extension called LTX. So and you click on the program. So without doing adding any sources, without running implementation, I mean synthesis implementation, if you directly have the bitstream that is provided by anyone, you can still run your you can just implement your circuit on FPGA, and you can do the real-time testing. So I have done in the similar manner. You can see again in the ILA, I was able to reproduce the same result. So this is the energy value. Whenever the energy value is high, we are getting a valid signal. And during the computation process, this energy value is directly coming from the energy register, and that is register is continuously getting updated at each and every clock cycle on arrival of a new sample. That means we are accumulating the resultant, right? Energy is equals to existing value plus square of the current sample. So like that, once a particular finite length has achieved, we set the length to be 8, right? After the 8 samples, the energy value is completed. So in this way, you can directly run the bitstream file without having any sources, provided that you are given with a bitstream file. So I hope this demonstration is also clear. Let me clear my workspace. So without wasting any further time, we will just proceed with the next example. Just give me a minute. Yeah, so we will proceed with the next concept, that is design, preparing a custom user-defined IP course. So for this, what I do is I take the example of logic gates. So let me present my screen first. I'll open my tab in this file. Yeah, Microsoft Word. So to keep it very simple, in order to, my main motivation is to explain you the concept of creating a user-defined custom IP course, but end application is not of main significance. In order to understand this concept, I just take a basic example of logic gates. So again, back to first day example, we have designed logic gates in Verilog. So AND, OR, inverter, so on and so forth. So how we have designed? We have designed in three level of abstraction. First we did it in gate level. Next what we have done, we have seen the data flow, and next we have taken behavioral. So next, what is meant by IP based design? So right from day one, we are using inbuilt IP course. So first of all, what is an IP? IP stands for intellectual property. And we also call it as IP core. So we call it as intellectual property core. So moving further, why why do we need an IP and what are its uses? That is very important. So we have seen what is a hardware design flow. So right from day one, what we are doing is we are collecting the specifications. That means yesterday we have seen, right? I want to design a hardware module that will calculate the energy of a signal. The energy of a signal means the signal has a finite length duration. The finite length and the length we denote it as a frame size, and signal size may vary from 80 to 1024 number of samples. So depending upon the signal size what I value, and depending upon the signal what I drive, it has to calculate the signal energy. So these are the specifications. This is a broad specification. If you narrow it down, we have given so many type of specifications that we discussed yesterday. So after getting the specifications, what we did, we tried to design the custom hardware in order to do the task in real time. So how did we design that custom hardware? First, we have that specifications we have converted into HDL description. How did we convert that specification into HDL description? By using Verilog language. After that, what we did, this HDL description, we have done synthesis. That means from the description, we try to get the RTL or gate level netlist. Once our netlist is fine, then what we did, we mapped this one to FPGA netlist by doing implementation, and from that what we did, we did a bitstream generation, and from that we programmed our FPGA, and on the FPGA we implemented our circuit in real time, and then we have deployed and we have operated. This is a conventional flow. So we, with the specifications, what we have done, we have designed a hardware using HDL description. So what is this HDL description again? So we have designed exclusively for to match with the specifications. So at each and every time, again, if you want to change any of these specifications, or if you just want to alter their characteristics, or if you want to alter any of the parameters, then what you have to do again, you have to go back to your HDL description and you have to make changes in the HDL description accordingly to realize a new hardware architecture. So every time the user needs to edit his HDL. So that means every time you need to rework on your Verilog codes, because and this is treated to be as a tedious process and it is cumbersome. Why? Because the underlying architecture will be more or less the same. Only thing is you are changing the parameters. Parameters in the sense, say for example, the same design what we have taken, frame energy, we have designed to calculate up to a signal with a maximum number of 1024 samples. Now, for this to represent the frame size, what we have taken input some 11 down to 0, we have hardwired the size input that is going to our module. Now if I ask you, I need to evaluate the energy of a signal wherein the signal will have samples up to 2048. Now what you have to do, the underlying concept is different, remains the same, but for this what you have to change, you have to change the size of the parameter. Why? Because earlier you have designed your HDL description by hardwiring it to meet the requirement of 10 to represent the size of 1024. Now you want to make it variable up to 2048. Now for that purpose again you need to increase the size from 12 down to 0. So like that you are making a changes. Now again, if I tell you one thing, earlier we considered all our frame samples, that means signal sample, to be of 16 bits. Now if I tell my signal is having 32-bit sample, it is a 32-bit sample, or else 8-bit sample, or else 11-bit sample. Now our architecture what we have designed earlier, it is for 16-bit. Now it will not work. So what we have to do, again the same architecture we need to redesign again by modifying the HDL script, and this time retargeting it for new specifications. That means input signal sample is of 8-bit or 11-bit or 16-bit or 24-bit or 32-bit. So what we are doing is we are for each and every time whenever any parameters keeps on changing, then the underlying concept will never change. If you want to calculate the energy, that m is equals to 0 to infinity x of m whole square, this equation will not change. If you are changing the frame size, this infinity upper limit will change. Earlier we calculated from 8 to 1024. This time I am increasing the range to 2048, means this limit is changing. So if this limit is changing, if any hardware associated with this limit, those parameters will change. Again, this energy value we have seen, we have represented with 25-bit, and this x of m value that we represented with 16-bit. Now if I change the input signal, if I tell that it is not 16 bit, if it is 32 bit, only the representation is changing, but underlying concept remains the same. When this representation is changing, ultimately your hardware either will go scale up or it will scale down. So what is meant by scale up or scale down? So if you will just take a register which is holding the value of a signal sample. Earlier your signal samples are all are 16 bit in length, so you need a register with 16 bits. Now you are telling that your signal length is, each sample length is 32 bit. Now what you are doing, your register size got increased from 16 bit to 32 bit. So only the hardware is scaling up or down with respect to these parameters. So in that case, however, underlying process is not affected. So if these parameters vary continuously from one application to another application, if you have a single piece of a hardware, then having a HDL description, when you're porting that type of architecture in different applications, what you have to do for each and every application, you have to re-edit your HDL script entirely. Now in our frame energy module, if you take the entire script, so for example, uh, where is the script? So how many lines of code this one? Maybe approximately 120 lines. Okay. So if you're dealing with a design that is having maybe up to 10,000 lines or 20,000 lines, then in that case it is a very cumbersome process. You cannot go into the script and you cannot edit always change the parameters with respect to one application to another application. So changing the parameter in the sense, see if this frame size is changing, again you need to change this. Buswork is fixed, right? 10 down to 0. Why we fixed that buswork to 10 down to 0? We want to represent frame size from 8 to 1024. To represent 1024 in binary, we require 11 bits. Now I will tell I need to scale it up to 2048, so it should be 12 bit. So again you have to go here and you have to manually change 10 down to 0 to 11 down to 0. Frame sample earlier we took a 15 down to 0, that is 16 bits. Now if I make this 32 bit, then here I have to make 31 down to 0. But not only if you change the port list, that is not sufficient. Why? Because this will affect the computation at the description level. Why? Because earlier we assumed that data size is 16 bit, and accordingly what we did in the frame energy, the product is 16 into 16. If you multiply two 16-bit numbers, the resultant is 32 bit. So product is 32 bit. So if you are making changes in one variable, that is frame size, you are making again 32 bit, then the product will be of 64 bit. So again you have to make changes over here, that is 64 bit. So once that is changed, this energy value representation, uh, this is of 25 bits, right? So this again will change. And the part selection, so we are selecting the part selection, right? So when we are multiplying two 16-bit number, we are getting 32-bit data. The 32-bit data fully we are not taking it. We are only converting the 32-bit data into again 16-bit data by doing a path selection, and that data what we did, we added to the accumulator register. So whenever any parameter is changing, everything, all the numericals and these internal parameters will change. But however, the logic will never change because the functionality remains the same. Logic will never change and these parameters will change. So if it is a 10,000 lines of code, then for one application to another application, you cannot change each, you cannot sit and change each and everything. So for that purpose, what we basically do is called either there is two concepts. One is the parameterization and the second concept is called uh, making an IP. So how to do parameterization? So that I will just explain. Uh, so before that, I just want to make a copy of this code. I will just paste it on desktop and I open it. So how to do parameterization means, so there are two types of parameters, global parameters and local parameters. The local parameters anyhow we have seen when we are designing an state machines. We have declared a local parameter and we set a parameter variable and its value. These are local parameters. Now what are global parameters? The global parameters, along with the port list, on top of the port list you have to define global parameters. So how do you define global parameters? After the module name you have to put a hash symbol and you have to open two parentheses, and remember there is no comma or a semicolon after the parenthesis. So this is a syntax, and after the opening brace you have to write a keyword called parameter. So that means here you are declaring all global parameters. So what is the first parameter means, I want to use a parameter called data width. Data width. So the data width I am giving maybe 16, say for example 16. So this data width is 16. That means the signal samples that are coming to my frame energy module, each sample is of 16 bit. Now here you can see where frame sample I have used it, right? Frame sample. Here what I can do is this is I had hardwired. I declared it hardwired like 15 down to 0. That is 16 bit. Now this I will make it a variable with respect to the parameter. This how I will define means data width -1 down to 0. So the data width value is 16. So 16 minus 1 is 15. 15 down to 0. That means again 16. So total 16 bits. Earlier we have written 15 down to 0. The same thing, data width is 16. 16 minus 1 is 15. 15 down to 0 is the frame sample width. So this is called as parameterization. So instead of representing hard wires, hard encoded values, we can use these parameters in order to so that again internally we created some registers, right? So for that registers also you can do this parameter, you can use this global parameters. Say for example here that we have a product, right? So in product what we are doing, the received samples we are squaring it. So if received sample has a word size of 16, then the resultant will be 2 times of that, so 32 bit. So for that what you are doing is here uh, data width data will -1 down to 0. So earlier we kept 31 down to 0. So data width is 16. So 16 plus 16, 32. 32 minus 1 is 31. So 31 down to 0 is again 32 bit length, and this is prod. So this is parameterization. Similarly, in the whatever the values, numerical values we have defined here, everything needs to be parameterized. So we have to manually calculate. If at all, if the data width size is varying, then what is the net effect? If the data width size is varying, then what are the limits of the maximum energy? What is the possible number of maximum energy that is going to come, and how we can represent without how we can represent that values without loss of without loss of without any loss in the representation, or without any drastic error. With minimum error, we how we can represent how many number of bits are required, that relations we have to find, and everything we need to represent these values in terms of these parameters. In that case, if you do like this, then at the top level itself, whenever you are using this module in different applications, if you want to change the parameters directly, you will change the parameters at this section, and accordingly your entire hardware architecture, the parameter values will be propagated, and at the time of synthesis, the widths of all the internal variables, that is either registers or wires, will be handled, and accordingly an appropriate hardware architecture will be realized with respect to the chosen parameters. So this is the concept of parameterization. And so then why do we use IP cores? So that is one more thing. So I have addressed the first concept, what is parameterization. The second concept is why we have to use an IP. Again, if you see, your though your code is parameterized in this manner, at each and every time you are trying opening your RTL code and you are editing all your parameters, sometimes there might be a chance like someone, you have given this to someone and you have asked it, and due to their due to without their notice, maybe they might have edited or changed any of the value within the code. Then entire architecture will be corrupted, because you won't be able to realize an architecture. So for that, what we do is uh, whenever you are handovering the designs from one team to another team, you will code it in the form of an IP block, and you will give it. So your RTL description, whatever you are written, it will be preserved and it won't be edited. Only the end user will be able to see on top of the architecture, there will be a IP customization window. In that window, the parameters are listed. Only in this pop-up dialog box window, the user can edit the parameters, and accordingly these values will be populated into the RTL code, and at the time of synthesis and implementation, an appropriate hardware architecture or a hardware circuit will be realized. So there won't be any scope in editing the RTL when you have transformed in the form of IP. Only the user will be having access to the GUI itself. He won't have access to your RTL description. So this is one thing. And second one, the main use of IP is one is anyhow you have seen this as customization. So customization is the main use, and second one is to generate an appropriate hardware. So this is the most important thing with the IPs. So one is customization that you will get either with IPs, even without using of a IPs. If you just parameterize your code, even this code is also customizable. So we can also call this RTL description as well as customizable RTL description. But advantage that we won't get with this parameterization, but the main advantage that we get with the IP is called hardware generation. So what is that one means? I will explain with one example. So let us take logic gates itself as one example. Now earlier what you have done, you have written your own HDL codes for each and every gate, right? So total there are I think 7 gates. So for each and every gate you have written your hardware description. Now what I do is I want to design an IP core with an input A and B and output C. Now in this IP core, I want an IP customization IP menu. In that menu, it will ask what is one parameter, what is the data width of each input and output ports. So this I would be able to customize. Next thing is I need a drop down menu where I can select my desired logic. It can be AND gate or an OR gate or a NAND gate or an OR gate, so on and so forth. So when I select one appropriate gate, then the IP should generate that particular hardware. So because this is the logic gates, I think this is a basic building block. These gates will be used throughout across many applications. Say for example, you just assume like that. So for each and every example, if I create gates by using a code, I'm just simply wasting my time. Why? Because instead of spending my time in the main part of the code, for each and every basic building blocks, I'm putting some time and writing codes for each and every logic gates. So instead, what I can do is I will put only one time effort. In that one time, I will club everything in the form of an IP core, and if I package it, then whenever I want to use anything, I'll just call my IP and I will customize in my IP menu like what is the architecture that I want to generate, and that architecture it needs to generate. So this is the second concept, generating the architecture. And how it is generating. First it will take the customization parameters on top and then it will generate accordingly. See, earlier you designed all gates are 2 input gates, that I agree, and each input is a 1 bit, right? Earlier you designed like this. Now in one application I want 4 bit AND gate. In other example, we need 7 bit AND gate. In other example, I need a 3 bit AND gate where each inputs are of 3 bits or 7 bits or 4 bits, so on and so forth. So for each and every application, I cannot design each every time. So for that, I will write a customized block, and like that for all the gates, I will club it into a single. I won't tell it is an architecture. I will club it into form of an IP core. From the IP core, what I will do is whenever I need, I will try to generate a architecture out of it. So this is the advantages of IP core. It generally saves time and it helps you to customize the architecture, and it also helps to generate the appropriate architecture as per your desired requirement. So I hope this much theory is sufficient and for the introduction about the IPs. Now my main motivation towards this experiment is I want to create logic gates IP core. This is a user defined custom IP core. So we will see how to design IP cores in Vivado. The flow is more or same across any FPGA based platforms. In any type of EDA tool, that is either from Xilinx FPGAs or Intel FPGAs. The EDA tool will vary, maybe Vivado or Altera Quartus or any other thing, but the flow remains the same. So I will just introduce you to the flow. Uh, so first, my main idea is to create individual logic gate codes. So first, earlier we have seen how to create a Verilog code file for the AND gate, right? I will explain with one example and we will replicate the same for everything. You can prefer any level of abstraction, either gate level or a data flow or else behavioral. So how the basic HDL description starts? So it starts with a module and a module indicate. Okay. And we have parentheses, semicolon, and how it looks like. So earlier what we have done, we have created input and output C, each of 1 bit. But now what I do is I will do just parameterization. So for that what I do, hash opening brace, and I will write a keyword called parameter, and my first parameter is data. Now dummy value I will give 2. Actually whatever the parameters and the values which you are giving here currently treated as dummy. When you pass the actual value to this data virtu value, then appropriate hardware architecture will be realized. Okay, so now the input data width I am going to specify with this parameter. So now it is no more a single bit input, it is a n bit input where n is given by the data virtu variable. So for this case what I do, input width -1 down to 0 and same thing, data width -1 down to 0, and for the output, so this is how it looks like. And for the description of AND gate I am using assign output C. I am using data flow modeling. C is equals to A and B. So this is a thing. So for this is a parameterized AND gate. Earlier we just written a normal AND gate, but this is a parameterized AND gate. In this parameterized AND gate, what we have done, however, this gate still has 2 inputs A, B and 1 output C, wherein the parameterization is applied for the to represent the data widths of these inputs and outputs. So if I keep data width 2, then I will get a 2 input A, 2 bit wide A input, 2 bit wide B input and 2 bit wide C output. Similarly, if I keep 4, I will get 4-bit wide A input, 4-bit wide B input, 4-bit wide C input. Now similarly what you do is design an OR gate. So keep a module name OR, and here you give X sorry A or B. Like that, what you can do, you can create NAND gate, and what you can do, A and B, you can put tilde symbol, that is negation at the prefix. And if you want NOR gate, you can change the module name to NOR, and here inside the bracket you keep A or B, outside you keep a negation. If you want XOR, you keep a XOR gate, and then A cap B, that is XOR. If you want XNOR, again change the module name to XNOR, and then this remains the same, A cap B, outside you keep a tilde. So like that, you generate 6 different files for each and everything. Make sure that module name and Verilog file name with extension .v should match. Earlier I have seen some people, students, file name is different and module name is different. That will create a mismatch. So create all these files separately. I have created at my end. So today is day 5. So lab 1. Sources 1. So I have created all the 6 gates of AND gate, OR gate, NAND, NOR, XOR, XNOR. So total 6 gates. OR gate I have not, sorry, NOT gate, inverter gate I have not done. Why? Because inverter has only one input, one output. But since we are making an IP with 2 inputs and 1 output, so not we cannot put it over here. We need to use the concept called dynamic input ports. That is little bit complicated, so that I'm skipping it as part of this FTP. So to keep it very much simple, I'm using only 6 gates. So however, there is a concept called dynamic port. So what is dynamic port, I will tell. So you have an IP, right? Now our IP is having 2 inputs fixed, 1 output. This is also fixed. Fixed inputs, fixed output. Sorry, fixed inputs and fixed outputs. Inside what we are doing is we are making IP customization menu. In this menu, we are providing an options for the end user, like to create AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate. So when a user selects any of this gate, then what it will do is to this black box, it has 2 inputs A, B and C, right? Inside it will create an appropriate gate and it will make connections. And that too, in the IP customization menu, we can also define what is the data width, right? So if data width is kept 4, then this line will be of 4 bits, this line will be 4 bits, this line will be 4 bits. So this is how the IP customization and generation is going to work. This is quite fixed ports. There is another concept called as dynamic ports. Dynamic inputs and dynamic outputs. So whereas in dynamic ports you have some compulsory inputs and some compulsory outputs, and you have some optional inputs, and you have some optional outputs. And in the IP customization window, you will have to define, you have to enable the user to configure inputs and outputs. So the user will select these optional inputs if he wants, and these are optional outputs if you want. So you have to provide some checkboxes, and you have to tell outputs. If you want this output, he will use it. If he wants a output, he will add it. If you want the output, he will add it, or if you don't want, he will uncheck it. So those are optional. So like that you will have optional inputs. So in that case, what if for the say for the same logic gates IP, what you have to do is A input you have to put a compulsory, and B input you have to put optional, and C output is compulsory. So in case of inverter, what you will do, B anyhow you kept optional, right? That you will disable. So only one input will come and one output will come, and then you can select AND gate. For rest of the case, since B is optional, so you will select it optional input. So you will have two inputs and you will have one output, and you can realize the rest of the gates. So this is the concept. Then if you are selecting optional inputs, optional outputs means not, don't think just like a checkbox. If you keep a checkbox, if you select a, it will add one extra output. That is not the case. For each and every option you have to generate a separate architecture, and you have to add it to the customization window. So whenever if you keep a checkbox, then that particular architecture is selected in order to generate a and realize a hardware. It's not just like if you keep a tick mark and output will be added directly or it will be removed directly. The IP customization menu may look simple, but in order to prepare that menu, it is a complex process that anyhow we will see how to do that. So as I mentioned you, I have already created the basic logic gates. Now what we are supposed to do is, in order to generate the IP, we need to create a top wrapper. So in the top wrapper, so we have individual RTL description codes for each and every gate, right? So in order to encompass all these things, we have to write a top wrapper, where in this wrapper we have to instantiate all these blocks, and this entire wrapper whatever we are having, that we need to transform into the IP core. So now how do you define that wrapper? So that I will explain you. So just create a new file. This time I will call it as logic gates IP. Wrapper name logic gates IP. What I will do is I will just open it in text editor. You can create a Xilinx project and you can do it over there as well. So wrapper is also a top module, so it will also have a keyword module. Module name is logic gates IP. That is our IP core that I want to design, and module. And as I said, any parameters. So that also will do. First parameter, that is data width, I want to give so some dummy value. As my main IP is nothing but a black box, it has two inputs, right? So A and B. This is the top module, and it has an output called C, and each input has width with minus. and inputs. The IP is ready. So this IP is ready. Input A, this is variable, it is n bit. Input B, this is also n bit, and output C, this is also n bit. So n is defined by data width parameter. Now there is one more parameter that I want to tell. What is the logic gate that I want to select? This is second parameter that I have added. This is on top module. So what is the logic gate? So what type of a logic gate I want to select? So the dummy parameter I give in the form of indicate. This logic gate parameter can be anything. So what are the valid values for the logic gate? So for the data width, what are the valid values? It can be n, that is any positive integer greater than 0. So data width cannot be 0, right? So what are the possible values of the data width? Any positive integer greater than 0. Similarly, what are the possible values for the logic gate parameter? So logic gate parameter, we have taken it as a string parameter. So what are the possible values? It is AND gate, OR gate, NAND gate, so on and so forth. So like that, 6 possible strings we are considering. So it can be any of those gates. Now, as I mentioned you earlier, IP means it helps you to customize the architecture with respect to some parameters. So here I am basically in my logic gates IP, I am providing you an option to customize one parameter. What is the parameter? Data width. So the width of my inputs and outputs can be customized by the user as desired. So to allow customization, what I did, I have given data width parameter to be 2. This is dummy value. In the IP customization menu, you can enter any value. That value will come to the data width parameter, and this value will be passed down to the architecture. And once you have customized your architecture, when you are generating it, this value will be used to appropriately generate a custom hardware. The second thing is, this is called customizing the architecture using an IP. The other use of an IP is to generate, right? Now in my IP core, logic IP core, I am asking the second parameter called what type of logic gate you want. So once the user specifies the desired logic gate, the IP will generate that appropriate logic gate. So this is called generation. So with respect to this logic gate, a particular architecture needs to be generated. So for that, in Verilog, we use a keyword. We use a block called a generate block. So the syntax goes as follows: generate and end generate. So inside the generator block, I am using case with end case. Inside the case, I am using the parameter called logic gate, and I am defining the cases. When the logic gate is AND gate, what it needs to do, begin and end. Similarly, when it is OR gate, what it is supposed to do, begin. I have to fill the statements within the begin and end. Similarly, if it is AND gate, what it is supposed to, so on and so forth. For all the gates, we will mention like this. Now what I have to do is, inside this block, I have to instantiate the AND gate logic that we have written earlier. So if you remember, so this is the AND gate logic you have written earlier, right? Let me open Visual Studio here. So this is the AND gate that you have written, right? So you have to do instantiation. You know how to do instantiation, right? In our test benches, you have instantiated your module as a design under test, right? So like that, you have to do instantiation. So you have to first copy the module, just to rearrange all these things. Now, so this is a module name AND gate, having parameter has this one. Now you need to remove the keyword parameter. This is absolute. And you have to do mapping, right? So before data width, you have to put a dot. After that, what is the value is there that you remove and put parenthesis. In the test bench, after you have instantiated, you have given an instance name, right? It is very much mandatory to give a unique instance name to each and every module. So for this, I am giving an instance name inst1. Instance name can be anything, you can give any name as such. And this notation input and the data width that I will remove. This is not in the instantiation. So I hope everyone are aware of what is the instantiation format. So the port names should be prefixed with a dot, and it should be suffixed with a parenthesis. So this is how instantiation. This entire instance belongs to one particular module instantiation that is treated as a single statement. So for a single statement, you don't require begin and end. This I have written earlier for your understanding, but single statement means you can skip the use of begin and end. If it is more than one statement, then only you have to put it in a finite block called begin and end. So now, if the user provides a logic gate variable as AND gate, then what it has to do? So the very top module has to instantiate the AND gate. And how this instantiation is working, while instantiation, the parameter value is top module. So top module is our IP, and at the bottom level we have our instantiation, and this gate requires a parameter of data width. This data width we will pass from the top module. So data width is passed by the top module, and a top module has an input A. To that input, what we have to do, we have to connect to the at the bottom level. Once after a AND gate is been instantiated successfully, the top module A input should be connected to the A input of the bottom level gate, and B input should be connected to B, and C input should be connected to C. So this is how the instantiation looks like. So I explained, right, same thing earlier what I have explained. So we have a IP block, we have an input A, input B, we have an output C. This is n bit wide, and n bit wide. This is parameter. This is mentioned by the determined by the data width parameter. And inside and the second parameter, what is the parameter? That is logic gate. When a user says I want uh, AND gate, so he selects AND gate, so AND gate will be realized. Even in the AND gate, this output is C, input is A, input is B. So from the top level design, A input should be connected to A of the gate at the bottom level, B input should be connected to B input, and C output at the bottom level of the gate should connect to the C output at the top level of the output of the IP core. So the same thing what I have represented in the diagram, that only I have instantiated, that only I have represented it in the form of a description over here. Now for the OR gate, what I do is the same thing I will just copy because the syntax is more or less the same. Then now the module name is OR gate. I will just change it to OR gate. Already we have declared AND gate and we have referenced it with a unique name called instance1. So again, we cannot use the same keyword or the unique name. You cannot refer to OR gate with the same unique name. You have to change the name to instance2. You can keep anything as you desire, no problem. Again, the connections remains the same. For the OR gate, if at all the user is selecting OR gate via this logic gate parameter, the data width from the top module will go to the data width, and ABC will be connected to the ABC of the OR gate. Similarly, you have to repeat this for NAND, NOR, next XOR and XNOR. If you do so, your final code looks like this. So this I have already done. Just a minute. So this I have already done. So logic gates, parameters, and port list. And in the generate and end generate module, inside the generate I used case and end case, and I have given the string names like AND gate, instance of an AND gate, OR gate, instance of OR gate, NAND gate, instance of NAND gate, NOR gate, instance of NOR gate, XOR gate, instance of XOR, XNOR, and instance of XNOR. And okay, here the names I have not written properly. AND gate instance 1, OR gate instance 2, NAND gate instance 3, NOR gate instance 4, XOR gate instance, XNOR gate instance. So these are the source files. Copy. Okay, 7 files. Yeah, These files, I think if you have designed it, then straight away you can use these files. Otherwise, I will do one thing. I will share these files to Dr. M. Mahesh sir, so you can just collect from him and try to follow up the experimentation along with me. So just give me 2 minutes. I will share these files. Mahesh sir, are you available, sir?
Yes, sir. Tell me, I am available.
Sir, I have shared the files to Mahesh sir. You please collect from him.
Yes, sir. I'll tell him to share to the students.
Okay.
Sir, after this, we'll start after the lunch break, sir.
Sir, please confirm once you have received the files.
Yeah, yes, sir.
So, dear participants, by the time you receive the files, what you can do is you can just create the end project environment. So, click on project, create a new folder like day 5. In the day 5, we are doing the lab 1. So, create a new folder for lab 1. Create next. Select your FPGA target to basis 3 and click on finish. So if at all your target language is VHDL, then just change it to Verilog. I hope you have received the files. So if you have received your files, then click on
Yes,
add
sir.
sources.
Yes, sir. They have received the files, all the
Okay.
files.
Okay, sir. So you can download those files and keep it on your desktop. And then what you do is from your project, click on add sources, add or create design sources. Now this time you click on add files. So what you do is from the available sources. So total there will be 6 gate files. So AND, OR, NAND, NOR, XNOR. So total 6. And the top module file that is called as logic gates ip.v. So you click on OK and then you click on finish. So a higher depending on the hierarchy which I have defined, so top will be selected automatically and at the bottom all the 6 logic gates will be instantiated. So you can just expand the design sources folder and you can see under the logic gates IP, this is a top module. If you just expand,
Sir,
you can see.
have you not shared the screen?
Oh, sorry.
Yes, sir. Yes, sir. So I thought you were giving the. Uh,
Now you can see, sir.
Yes, sir. Yes, sir. Yes, sir. I
Hello.
thought you were just giving the
Okay.
instructions. Why not? Okay, sir.
Okay. Sorry.
Yeah, fine, sir. No problem.
Yeah. I have done only the same thing, add sources, add or create design sources, add files. So you just source all those files and you add it. Once you have added in the sources folder, in the design sources folder, you can, hello. Okay. Under the design sources folder, you can see the top module will be selected automatically, logic gates IP. And under this, you can
Hello, sir.
see, yes. Anyone has any problem? Hello?
No, sir. This is just
No,
a
sir. No,
disturbance. Sorry, sir.
Okay. I'm getting a echo signal. That's why. Fine. Yeah. Under the logic gates IP, you can see the instantiation of AND gate, OR gate, NAND, NOR, XOR, XNOR. So you can get parameter, input, output, and we have a generate statement, case statement. For AND gate, we have done use the instance of an AND gate, OR gate, instance of an OR gate, NAND gate, instance of NAND, NOR, XOR, XNOR. So that's it. I hope everyone has completed up to till this step. Uh, so now we need to transform this logic. You have to click on tools. You can see create and package new IP. So if create and package new IP, new IP definition. So click on next, and it is asking you where to package your IP. So it has identified a default path, so don't disturb the default path. So you leave it to default. It is this is a directory related to your current project. So you just click on next, and next it is giving you the new IP creation summary. If you want, you can just go through the details and you can click on finish. So once you click on finish, you will be getting an IP packager window. So this is how the IP packager window looks like. So if you just maximize, you can see here we have the packaging steps right from 1, 2, 3, 4, 5, 6, 7, 8 steps. So first we are in the identification step. So in under the identification, we have a set of parameters. So identification in the sense, how do we need to identify your IP core? So all the necessary information with respect to the identification, you need to give it. Here there are no much technical details. It is only just a theoretical details. It is asking who is the vendor of the IP. By default, it is given xilinx.com. You can give a vendor maybe your institute. So what is your institute email website? Let me Google it. If I'm not wrong, this is your institute website, right? So
Yeah, right,
mits.ac.in.
sir. Right, sir.
Yeah. So for example, we assume like the vendor is mits.ac.in. So xilinx.com I will remove and I will place so mits.ac.in. And in which library I need to package and create this IP. So I'm leaving it to default in the user library. I'm asking it to package. And what is the name of the IP? So name of the IP, it has automatically taken with reference to my top module name. So top module name I kept it as logic gates IP. So directly it has taken logic gates IP. So what is the version of my IP? So initially I'm creating this IP for the first time. So that's why I'm referring it as version 1.0. In future, you may upgrade your IP. When you're upgrading your IP, you can give your own versions, maybe 1.1, 1.2, or 2.0, 2.1, so on and so forth. Then, whenever you're using your IP in the block design, what name it needs to reflect, that is what it is asking. What is the display name? You want a name followed by version. By default, it has taken like that, name followed by version. So logic gates IP underscore V version 1.0. So V1 underscore 0. If you want to change, you can change, otherwise you can just leave it. So description is also, it has taken by default. Next, what is the vendor display name? So you need to give the, earlier you have given vendor website name. So here you have to give the complete name of your vendor. So what is the complete name of your vendor? Say for example, Madanapalle Institute of Technology and Science. So that only I will enter it here. I don't know whether it will take ampersand symbol or not. That's why for safer side I have used the text itself. And it is asking the company URL. So the company URL is, along with the HTTP you have to enter. So https colon slash slash www.mits.ac.in. So this is the root directory of the IP, and XML component file directory is also given. So you need not do anything. So identification step has been completed. Next, go to the compatibility. For as of now, you can skip this one. So only thing is it is asking like for which FPGAs, which family of Xilinx FPGAs you are going to provide the compatibility for your IP for use in those for direct deployment on those FPGAs.
Hey everybody.
So by default, I think it has selected all the FPGA families of Xilinx. You can also specifically target any particular family or group of Xilinx FPGAs. So this is not a major step you need to worry about. You can skip it. Next is the files group. So when you are packaging the IP, along with the IP, what are the associated files that it needs to include in the package? So that is what it is asking. Again, this is also not a mandatory step, you can just skip it. Make sure like for each and every step, this adjacent to it, a green color tick mark is available or not. If tick marks are not available, then you cannot package the IP. So at least you need to go to that step and you need to get out of that step without modifying any, without changing any options in order to get the tick mark. Next, there is a customization parameters. So in our module, we have given two customization parameters. One is data width, other one is a logic gate. So it is displaying those parameters. If you want to edit those options, you can still edit. I will tell you how to edit those options. Next, if you click on port and interfaces, it is showing you what are the types of ports and interfaces you are having. As of now, all the ports are compulsory ports. Earlier, I told like you can make some ports to be optional and all. In order to make those things, you have to edit the properties of each and every port. But however, to keep it simple for this FTP, we are not discussing about dynamic ports. We are only discussing about fixed ports. So you need not do any editing option here. In future, if you want to check, you can just check it. If time permits, I will just show you how to do it. And the next one is the addressing and memory. And since in our IP core we don't have any memory kind of elements, and we don't have any addressing and memory mapping kind of mechanism. So if at all in your designs, if those things are there, we have to create a memory map and addresses for each and every device and all. So in our case, this is not mandatory or necessary. You can skip it. Last one is the customization GUI. So if you remember, inbuilt IP cores, whatever we have used from the Xilinx, we have used the Xilinx clocking wizard IP core, in ILA, integrated logic analyzer IP core, and virtual input output IP core. If you remember, whenever we used an IP, existing IP, we have double clicked on the IP to get a customization window. In that customization window on the left hand side, you would have seen the IP block diagram. On the right hand side, you have seen the customization menu. So similarly, for our user design, we are able to check how our customization window, that is GUI interface, is going to look like after when you package your IP. So it is just showing you the layout. Here in the preview section, you have your IP block, inputs A and input B, output C. In the IP customization window, you got the component name, and here you have the data width parameter and logic gate parameter. By default, you can see data width parameter came as a editable text box. So you can edit the values over here by giving your desired port size or data width or desired value for the parameter. But if you see in the logic gate, again here we got as a editable parameter, whereas the parameter value is given in the form of a string, AND gate or gate, so on and so forth. But what I told you earlier is I want this in the form of a drop down menu. So how to get a drop down menu out of it? So for that, what we have to do, we have to go back to our customization parameters, and here you can see logic gate is there. If you double click on it, you will get a one edit IP parameter. So here you have to do few editings. If you do those editings, then this text box can be converted into a drop down menu, and from that menu you will be able to select each and every individual architecture separately. I think now the time is 1 o'clock. We will take a lunch break and we will get back after 1 hour, maybe at 2 o'clock. At that time, we will see how to edit the customization parameters, how to package it. After packaging the IP, we will see how to use it in our application and how to deploy it on FPGA. So I will conclude, I will just stop the session over here and we shall continue our discussion after the lunch break.
Okay, sir. We will continue at 2 p.m. sir.
Okay, sir. Please try to come by sharp 2 o'clock. Why? Because since today is the last day, we have few more topics for discussion. We will try to wind it up so that anyhow video recordings will be available for you even after the end of the FTP. You can go through these video lectures and you can practice.
Yeah, okay, sir. We'll be assembling at 2 o'clock, sir.
Okay, okay, sir. Thank you very much.
Thank you very much, sir.
I'm yeah.
Thank you, sir.